Bismillahirrahmanirrahim. I again welcome you all in the course of heat and mass transfer. This is lecture number 9. Dear students, today we solve, inshallah, the problem regarding transient conductions. The previous lecture I have given you the theory about the transient conduction and where the lumped capacitance model can be applied where the Biot number is less than 0.1. And of course, we're talking of that the temperature gradient within the solid body is negligible. So let's solve the problems. Predicting the time of death. This is a very approximate problem, which I have which I think it is good to know to you to have a practical application in predicting the time of a death of a person. A person is found dead at 5 p.m. in a room whose temperature is 20 degrees Celsius. The temperature of the body is measured to be 25 degrees Celsius when found. When the body is found, its temperature was 25 degrees Celsius, and the heat transfer coefficient is estimated to be 8 watt per meter square per degree Celsius. Modeling the body as a 30 centimeter dia and 1.7 meter long cylinder. Of course, this is an approximation to make this the geometry parameters easy. Estimate the time of death of the person. Okay, students, the body can be modeled that is mentioned in the problem, and again, it is one of the approximation which is very quite relevant approximation. The diameter is 30 centimeter and 1.7 meter long. For example, a person. It's about 5 feet 6 inches almost. The thermal properties of the body and the heat transfer coefficients are constants. We are taking these assumptions. Of course, the radiation the effects are negligible. The person was healthy, and its initial temperature of the body is about 37 degrees Celsius. The average human body is about 72% water by mass. Thus, we can assume the body to have the properties of water. Right? These are our assumptions. So let's solve the problem. Of course, the T infinity is 20 K is 20 degrees Celsius, and the temperature of the body is 25 degrees Celsius. The temperature of the body initially 37 degrees Celsius. We have given the convective heat transfer coefficient. I have taken the specific heat of water 4,200 joules per kilogram degree Celsius, and the density of water is 1,000 kilogram per meter cube. The K, the thermoconductivity of water, is 0.617 watt per meter Kelvin. So first of all, I find the value of LC, the characteristic length, then I find the Biot number. Then after the Biot number, I can find the temperature from the relation 5.6, I think so. So from that we have developed in the previous lecture. So it's the volume LCV by AS. So volume is pi r square L, and this is 2 pi RL plus these are the two surface area at the end, which is pi r squared times 2. By simplification, I get LR by 2L plus R. I put the values of the length and radius. I get the value of the characteristic length of 0.0689 meter. Now the Biot number is LC by K. It's 8 into 0.0689 divided by 0.617. You see the Biot number is 0.893, which is less than 1, but it is not exactly less than the 0.1. But approximately, I'm finding this. I'm solving this problem and trying to find the time. So we know that it's a rho VIC by HAS. So V by AS is the characteristic length. So it's rho LC. C is the specific heat, or H ln Ti minus T infinity. Okay, putting the values of which is 1,000 density, 4,200 specific heat, and 0.0689. Right, is the characteristic length, of course, and divided by 8 is the convective heat transfer. It is the conductivity, I think so. So that is the values I put here. H is given to me, and I put the values here. I get the value is about ln. This is ln 37 minus 28 minus 20. Sorry, 25 minus 20. We get the time is about 12 hours 12.298 hours or 12 hours and 80 minutes. So the death occurred approximately 4:42 p.m. So this is the example just done for you how to apply this transient conduction problem in reality. Let's solve some book problems. A steel balls 12 millimeter in diameter are annealed by heating to 1150 K and then slowly cooling to 400 K in an air environment for which in time, of course, temperature infinity, environmental temperature is 325 Kelvin and convective heat transfer coefficient is 20 watt per meter square Kelvin. Assuming the properties of the steel to be K is 40 watt per meter Kelvin, the density is 7800 kilogram per meter cube, and the specific heat is 600 joules per kilogram Kelvin. Estimate the time required for the cooling process. We need to find the time for the cooling process. We have given the cooling process means from 1150 K to 400 K. We have given the environmental temperature is 325. We have given the H and K values. So it's a very simple question. The steel ball, right? Its diameter is 0.012. We are given the, of course, the initial temperature and then thermoconductivity, density, and the specific heat. The environmental temperature is 325 and H is equal to 20 watt per meter square. First of all, I find the Biot number is LC by K. And of course, the steel balls are spheres. 4 upon 3 pi r cube is the volume and 4 pi r square is surface area. So we get R naught by 3. So the Biot number is HLC upon K, right? Or it's a diameter by 6 or radius by 3. I get the value is 0.001, which is less than 0.1. So the capacitance model can be used. The time is rho VC upon HAS. Is the LNTI minus T infinity, T minus T infinity. I don't know the value of rho. I know the value of LC and the capacitance and the convective heat transfer coefficient and all the temperatures. So I put the values here and find the temperature, the time, which is about 1122.2 seconds, which is 18 minutes and 47 seconds. So due to the large value of course, the TI, radiation effects are likely to be significant during the early portion of the transient. Of course, we have ignored the transient effects, but of course, because the temperature are very large, we have to take the transient effects initially, but this is also a good approximated value. The next problem. Let's continue the problem 5-7. Consider the steel ball of this previous problem 5.6, except now the air temperature increases with time as T infinity T is a function of time is 325 K plus AT, where A is a constant which is 0.1875 Kelvin per second. Sketch the ball temperature versus time when T is from 0 to 1 hour. Also show the ambient temperature T infinity in your graph and explains special features of the ball temperature behavior. Find an expression for the ball temperature as a function of time T and plot the ball temperature from 0 to 1 hour. Was the sketch is correct or not, that you have to find out. So here the temperature is a function of time, as you know that temperature in the day is changing with the time. Of course, the morning is a low temperature, and we move towards the afternoon. The temperature is increasing, and then it's decreasing. This is a linear relationship. So what we have of course again the steel ball. The initial temperature is 1150, diameter is 0.012. The value of K is about 40 watt per meter Kelvin. Right, so rho is 7,800 kilogram per meter cube. Specific heat 600 joules per kilogram per Kelvin. The air ambient temperature is 325 K plus 0.1875 of T. What assumption that I'm making is the constant properties and negligible radiation heat transfer. So now I find the Biot numbers, whether this lumped capacitance model is applicable or not. So it's HLC by K. We have find LC in the previous problem. For the sphere is R naught by 3 or D by 6. So 20 into 0.002 divided by 40, we get 0.01, which is less than 0.1. It can be applied. So Now we have to do the energy balance, of course. Minus HAS T minus T infinity is equal to rho Vc dt by T, because here the temperature is, in ambient temperature, is a function of time. So let's introduce theta is the temperature difference T minus T naught. Of course, d theta is equal to dt. So is minus HAS. If I put the value of T325 plus 0.1875 T, small t is the time and capital T is the temperature, minus T naught is a rho Vc dt by dt. So it becomes minus HAS, right? So it becomes this minus this, of course. This becomes theta, this T minus T naught, theta minus 0.1875 T rho V, and dt is equal to d theta, so it becomes d theta by T dt. This is my equation number 1. Now we can this equation 1 can also be written as like this: d theta by dt is equal to minus k theta minus 0.1875 T. I have taken this one, this constant rho Vc over HAS. This HAS by rho Vc we take it as a constant, because H is a convective heat transfer coefficient, A is the surface area, rho is the density, V is the volume, and C is the specific heat, which are constants. In this question, I cannot separate the time and the theta. There's a temperature difference. So in this problem, variable separable method cannot be applied. So from your previous knowledge of calculus, in that case, of course, the value of this solution will be, one is the harmonic solution and other one is a particular solution. So one is the homogeneous solution, or other one is the particular solution. Homogeneous solution, when you put this equation equal to 0. So I write the d theta by dt plus k theta is equal to kat. This is my equation number 2. The homogeneous solution is, of course, we have one of the root which is minus k, right? So it is theta h is equal to c1 is a constant, e raised to power minus kt. You know that when the homogeneous solution, it is c1 e raised to power minus first root, e raised to power minus second root is equal to 0. Basically this becomes m plus k. If I say this was m, the linear equation, plus k is equal to m is equal to minus k, c1 e raised to power minus kt. This is my homogeneous solution. Now the challenging thing is the particular solution, because you have forgotten that we have studied in the previous classes. If you see on the right side of the equation, you will see what is the function on the right side. In our case, the function is a linear equation, so we can assume the particular solution a plus bt. Even though a is 0 in our case, but we have to take it into account, right? So I find out theta dot p, which is equal to b, and we put these values in the differential equation. In the given differential equation, theta dot plus k theta is equal to kt, theta dot is equal to b plus k, and theta is equal to ka plus b is equal to kat. Now we compare the coefficients of the constants and the t, and we find the value of a and b. If I coefficient of t, then of course this will be is equal to kb is equal to ka, and b is equal to a. And by comparing the constants, of course, it is b is equal to 0. I think so. No, so b is equal to a, sorry. And then I compare the constants. So constant is equal to ka, right? So we have to find value of ka. Ka is equal to, of course, minus a. This implies a is equal to minus a by k. So this is the way how you can compare these parameters. Now we can find out because b plus ka is equal to 0, so ka is equal to b is minus a, and then we get, so theta p is equal to, that particular solution is minus a by k plus at. That is right, because we have assumed a plus bt, so minus which is equal to A T minus 1 by K. So the total solution, the temperature difference as a function of time is equal to C1 e raised to power minus KT plus A T minus 1 by K. This C1 is an integrating constant that we will find with initial conditions. At T is equal to 0, T is equal to Ti. I put the value here, which is theta is T minus Ti. So T minus T naught, sorry. So it is Ti minus T naught, C1 plus A raised to a minus 1 by K, because at T approaches to 0, this becomes 1. So you get the value of C1 Ti minus T naught plus A by K. Now I put the value in this equation to find the final solution, and that is the solution of that is the temperature, how it changes with time. T is of course the initial temperature, T naught is of course the initial the given temperature, and A and K are the constants, and we put the values, and I can plot this graph. So when I plot this graph, if you see here, on the x-axis there is a time, on the y-axis there is a temperature. So if you see the ambient conditions, of course, a straight line, right? So it is moving like straight line, it's a dotted line, and then the sphere temperature, if you see, it is decreasing. First of all, it is decreasing, and then it becomes slightly increased and becomes constant. At this point, if you see, at this point is about at time T is equal to 1100 seconds. Both the temperatures of the ambient and sphere are in equilibrium. So for a small time, when T is less than 600 seconds, the sphere temperature decreases, right? Sphere temperature is decreasing, right? And at T is approaches to 1100 seconds, right? They are T is equal to T infinity, and dt by T is 0, which is very clear from the graph here. About 1100 it is 0. And similarly, if you see, at T is greater than 1100, the temperature of the sphere becomes decreasing with the as compared to the environment. And as for a large time of T minus T infinity and dt by dt are almost constant. Now they are becoming almost parallel to each other. So of course initially which is very clear, the sphere temperature is decreasing rapidly, right? And rapidly by 600, and then it becomes gradually slow, and at 1100 seconds both of them are in equilibrium, and later on the temperature of the ball is lower as compared to the environment, which is very much in reality. Dear student, for your help again I am solving one more problem, 5.5. For each of the following cases, determine an appropriate characteristic length LC and the corresponding Biot number is Bi that is associated with the transient thermal response of the solid object. State whether the lumped capacitance approximation is valid. If temperature information is not provided, evaluate properties at 300 K. If the properties are not available, then you can take the values of that particular properties at 300 Kelvin. The first case is a toroidal shape of diameter d is equal to 5 millimeter, and a cross-sectional area of is 5 millimeter square, is of thermal conductivity K is 2.3 watt per meter Kelvin. The surface of the torus is exposed to a coolant corresponding to a convection coefficient is also given to you 50 watt per meter square. So I need to find out the Biot number. For the Biot number, the only challenging thing is to find the characteristic length. Dear students, actually you must be very much clear about this, that you have to find out the volume of this toroidal, and then you have to find out the surface area. So I have given the value of diameters, the cross-sectional area, the thermal conductivity, convective heat transfer coefficient. LC is equal to V by AS. First of all, pi d volume. Of course, volume is the cross-sectional area times the length. If you cut this toroidal, it becomes a cylinder. So the average diameter is given to you d. So the height becomes is 2 pi r or pi d, right? 2 pi r or pi d, and this the base area is the cross sectional area of pi by 4 d square. Small d is the diameter of this wire or thickness of this toroidal, right? So pi d AC is the volume, and then I write the surface area, which is more confusing for the students. So let's see first of all again, when I open up, by cutting by open up, this becomes a cylinder, of course, and the cylinder of length is pi d, right? And the circumference length is pi small d. Small d is the diameter that I am taking of this wire or toroidal thickness, right? So it is pi d times pi d. So now what is d? Because we have given the cross-sectional area. So AC is equal to pi by 4 d square, right? And d square is equal to 4 AC by pi, right? And d is equal to 2 times under root of AC by pi. I put this value of LC in this equation, right? In the given equation, and then LC is equal to, of course, this pi d cancel. LC is equal to pi 2 under root AC by 3 becomes half under root AC by pi is equal to 1 by 2. It's 5 by pi is 0.633 millimeters. Now the Biot number is LC by K, which is equal to 50. And of course, I put the value of characteristic length and get this 0.013 is less than 0.1. Lumped capacitance model can be applied. So the most important thing to find the surface area and the volume, to find the LC, and the only challenging thing is in these type of questions. The next question, a long hot AISA 304 stainless steel bar of rectangular cross section has dimension of W is equal to 3 millimeter and capital W is 5 millimeter and length is equal to 100 millimeter. The bar is associated to a coolant that provides a heat transfer coefficient of H is equal to 15 watt per meter square Kelvin at all exposed surfaces. And that which I have shown you, these are the pink colors, these are exposed surfaces. This is the W, the width, and this is the small w. So it is a rectangular cross section, that is square. So first of all, again, we have to find out the characteristic length. The characteristic length in this case, base area into height is the volume, W into W is the cross section area multiplied by length. This becomes the volume, right? And the surface area, of course, one side is this W into L 2 times. This is the of course the small w into L is the second side with 2 times, and then W into W, which is the other 2 sides. Right, so I have written very clearly here, it's 2 times W into W plus W into L plus W into L. You know that the rectangular ball will have a 6 sides, so they are similar. So I put it twice and then put just the values. I get 0.9 mm is my characteristic length. The value of K I have rendered from the table from ASI 30 steel, of course at 300 Kelvin. So that value is about 14.9 watt per meter Kelvin. I put in the value of HLC by K. I get 9 exponent minus 4.0009, which is less than 0.1. So therefore, lumped capacitance model can be applied. So the challenging thing is the volume and AS should be taken correctly. The next question is a long extruded aluminium alloy 2024 tube of inner and outer dimensions are W 20 millimeter and outer one is W 24 millimeter respectively. Is suddenly submerged in water, resulting in a convection coefficient of H 37 watt per meter square Kelvin at the 4 exterior tube surfaces. At the 4 exterior tube surfaces, the tube is plugged at both ends, trapping stagnant air inside the tube. So we will not take the ends in this case because only the heat transfer takes place from the surfaces. So the outer width is capital W, the inner width is small w, the length is of course L. Again, the challenging thing is to find the volume. So in this case, the volume, of course, if you see the capital, the outer one is W square, and of course the inner one is small w square. This becomes base area, right? Base area and then the length. The outer surface, because the heat transfer takes from the outer surface only, right? Not the inner surface. So it is capital W, right? So it is capital W times L, and we have 4 surfaces. We multiply with 4. So just put the values. I get the value of again the Biot number, which is 3.8 exponent minus 4.00038 with less than 0.1, and hence lumped capacitance model can be applied for this case as well. So let's see the next one. In this case, the length of the cylinder is about 300 millimeter long solid stainless steel rod of a diameter is about 13 millimeter, and the mass is 0.328 kilogram, is exposed to a convection coefficient of is 30 watt per meter square Kelvin. Again, the mass is given to you, the diameter is given to you, the length is given to you from the outer surface, right? So it is just like a cylinder, of course. So it's pi by 4 d square L, that is the surface area into length. Then pi dl is the surface area, this one, the curved surface area, and the two ends is of course pi by 4 d square times 2. And then I know the d and l, I put the value of this, I get 3.18. The next only thing is I need the, for example, the density. So I find density is a mass per unit volume, and the density is 8237 kilogram per meter cube. For this density, actually I need the value of K, so I get the value of K is 13.4 watt per meter Kelvin from the tables. So the Biot number is HLC by K, and I need the, just put the values here, I get 3.6 exponent minus 3 less than 0.1. Again, lumped capacitance model can be applied. So students, you see that the most important thing is to find the characteristic length, and for the characteristic length you must have a very clear idea of a volume is the base area into height and the surface area from where the heat transfer takes place. A solid sphere of diameter d is equal to 12 millimeter and thermal conductivity is 120 watt per meter Kelvin is suspended in a large vacuum oven with the internal wall temperature of the temperature surrounding is 20 degrees Celsius. The initial sphere temperature is 100 degrees Celsius and its emissivity is 0.73. So it is in vacuum, of course the heat transfer takes place through the radiation. So again I find the characteristic length, volume of sphere is 4 upon 3 pi r cube and surface area is 4 pi r square r by 3 or d by 6. Right, as it is radiation, so I have to find out the radiative heat transfer. It is emissivity, Stephen-Boltzmann constants, surface temperature plus the surrounding temperature, Th square plus T surface square whole square. This we have discussed in chapter number 1, right? So I just put the values of the temperatures, the surface temperature and the surrounding temperature, which is the T infinity. I get the radiative heat transfer coefficient 6.2 watt per meter square Kelvin, and I know now LC and K. I find out the Biot number is 1.03 x minus 4, which is less than 0.1. Again, a lumped capacitance model can be applied. So how I find out where I have to use the radiation, because it's a vacuum, and in the vacuum the heat transfer can only takes place only by radiation. The next is a long cylinder rod of diameters is 20 millimeter. Density is of course 2300 kilogram per meter cube. Specific heat or C, I think CP in the case of solid there is only specific heat, there is no CV and CB. So 1750 joules per kilogram Kelvin, and thermal conductivity of K is 1600 watt per meter Kelvin is suddenly exposed to a convective radiation with T infinity is equal to 20 degrees Celsius. The rod is initially at a uniform temperature of 200 degrees Celsius and reaches a specially average temperature of 100 degrees Celsius at T is equal to 225. So this is the cylinder, of course, and the pink color is of course showing that the heat transfer takes place through this. So we have given the volume for pi by 4 d square times L pi dl. There is no heat transfer from the ends, so therefore it is d by 4, or we get the 0.25 by 20. So 5 millimeter. So we need to find the convective heat transfer coefficient. We can find out from the equation 5.5. This rho VC AST, we have given Ti minus T infinity over T minus T infinity. We have all the temperatures, the density and the volume, and we have we have calculated the characteristic length, the specific heat, and of course the T, also the thickness, right? So I just T means here the length, of course. We just put the value and then we get the final things, right? The T that is time, and time I put the value of T here, I find the result, that is H is equal to this much. Now the Biot number, of course, HLC by K, only unknown is here was H, and the LC K is already known. I put the values 0.023, of course, less than 0.1. So of course lumped capacitance model can also be applied for this case. Now repeat the problem F, it says, but now consider a rod diameter of 200 millimeter. So only the same problem, of course, but the diameter has been increased, right? So of course we can find out the convective heat transfer coefficient, but just by comparing these two, all other parameters in this case of H, rho, V, C, A, S, T are to be cancel out, right? These are the Ti minus T infinity, T minus. The only thing is that is the V by AS, which is characteristic length, and that is the diameter, which plays the role in the difference of the convective heat transfer coefficients. So by comparing these two, I write H1 by H2. Means I write completely H1 is equal to rho 0.25 D1 C by T, and then this temperature. Similarly for H2, I divide both of them, I get the relationship between only the diameters, right? So H1 by H2 is equal to D1 by D2. I know the value of H1, which is 2.53. H2 is unknown. This is 20 initial diameter in the section F, right? Problem part F, and there's 200 is the diameter. In this case, I get it, of course, 725.3 watt per meter square Kelvin. Of course, the diameter increased, surface area increased, the convective heat transfer should be increased. So the Biot number is equal to HLC by K. I put the values, of course, all. I know the value of H now, LC, and I get 2.26, which is greater than 0.1. So in this case, lumped capacitance, of course, method cannot be applied. So you see that when the characteristic length becomes larger, then of course it becomes when convective heat transfer coefficient becomes larger or characteristic become larger, of course the Biot number might increase to 0.1, and in those cases it cannot be applied. So thank you very much. I hope the students you have a good knowledge from this, and this lecture will help you in understanding the some difficult concepts of the heat and mass transfer. My next lecture will be in the convection. First of all, I will discuss the what is convection and the three boundary layers. That is velocity boundary layer, which is a hydrodynamic boundary layer. Then I discuss the thermal boundary layer. Then I talk the concentration boundary layer, and then I go to the dimensionless number. So keep watching my channel, and you will get very knowledgeable stuff here in my lecture number 10. Thank you.